Greetings everybody, and I've got an update to the ultra low power clock that I did. It's actually nearly I think it must be 4 or 5 years ago since I did the last one and did a video about it. As you may remember, that clock was based on a PIC24, and it's back in 2017, and it was 5.5 microwatts that it was running, and it's at 3 volts, so basically off of essentially a lithium button cell, and we're just going to see if we can do any better than that, and let's see if we can actually really get into nanowatts, in other words less than 1 microwatt. So I'll just do a quick update to recap on some considerations for doing ultra low power stuff. One of the things is with microcontrollers is to keep the sleep current really in the tens of nanoamps, if not better. There's some PICs which go into picoamps, interestingly all based on quite old technologies, which is quite impressive, but tens of nanoamps is good enough if we're talking about running off button cells. And we also, to run a clock, we need to have the certain peripherals active, so LCD for example, I/O, so we've got some buttons to update the time, etc., and some means of timing, so that we have a way to actually keep time, and optionally the watchdog timer and brownout reset. For now we'll just deal with the LCD, the buttons, and the RTC or timer, should we say. And we really need to, when the clock's actually active, in other words, the microcontroller, is actually active, and the CPU is actually doing things out of sleep and it's woken up, is you want to choose the lowest duty cycle and the lowest microamps per megahertz. So that means that when it comes out of sleep, doesn't necessarily have to be the slowest or the fastest that the chip will run at, but it's the one that is the most efficient. And also you need to consider something which I don't think I've put in here, is what the startup time is when you're going out of sleep. So that's taken into account in this design, but I'm just mentioning that because if it's going to take you a couple of milliseconds to wake up from sleep, that's actually can be quite expensive. Oh yes, I did put in here fastest wake up time. In this particular scenario it takes about 10 microseconds for this implementation to wake up. And we also want to consider anything that's got a biasing network in it, so basically resistors, and that particularly affects things like the LCD. So if you're running it in multiplex mode, essentially you're going to have some sort of biasing network, and biasing networks are expensive because you have to have resistors across the supply rails to provide, basically as a potential divider, and that's going to suck out current. So we're actually running this in static rather than multiplex mode, the LCD, and that means that we don't have to worry about using biasing networks, because we can just go up to up and down between the power rails. On-chip regulators, any MCU that has an on-chip regulator, just really beware of those. Something which I hadn't been aware of earlier is that the on-chip regulators, of course, they need a biasing network as well. So anything that's got potentially a VCAP, for example, quite a lot of microchip devices have a VCAP on them. They'll have an on-chip regulator, and they can be quite power hungry, so I recommend just keeping that in mind. But since 2017 there have been some new external LDOs that have become available with very low quiescent current, down to 20 nanoamps, which I'll discuss shortly. And also, this actually goes back to these on-chip regulators. One thing that I have noticed is that when you go into sleep and it's relying on a low power mode for the voltage for the on-chip regulators, it could be existing, the actual sleep current could be being taken out of VCAP and not out of VDD. So for example, when you switch into sleep mode on with using the regulator, what will happen is that the device will, the core will drop down from say 1.8 volts and drop down to say 1.2 volts. And in doing so, while it might take maybe tens of seconds for the VCAP voltage on the voltage regulator output to drop. Now during that time you'll see a very low amount of current being drawn, and you could be drawn to the conclusion that the sleep current is really low. But as soon as that VCAP voltage gets within regulation voltage again, so down to say 1.2 volts if that's the low power regulation voltage, you're going to find that it's going to boost up again. So it might look reasonably low for say tens of seconds, and then suddenly you'll find a significant increase. So anything with an on-chip voltage regulator, be very aware of. So I mentioned at the beginning of these static LCDs, and also any chip that's got VBAT. So that's essentially a backup battery. Not always a good thing. I was looking at some more modern PICs than we're going to use in this one, in this particular design, and they had a VBAT, and the VBAT was taking about over a microamp. And well, we're kind of looking to see if we can take less than a microamp for the whole thing, not even in a VBAT mode. So that's of some concern. Just be aware, it's a similar thing to the on-chip regulators and the VBAT, because there has to be some sort of mechanism to switch between the normal voltage, normal power supply operating, and VBAT. And I suspect there's various bits and pieces in there which themselves take a little bit of current. This isn't necessarily a problem if you're not really going down to the sort of less than a microwatt or less than say 10 microwatts, but it is a problem if you are looking at the sort of currents and powers we're talking about here. And one thing that I think I mentioned before, and I keep going on about this, is board cleaning. You really must make sure your boards are clean if you're making a PCB. On these breadboards, it's not so much a big deal, except because a number of these devices that I've put in here are on breakout boards. They do need to have, those boards do need to be cleaned. And you can have very sporadic current measurements, which really is difficult to understand what's going on, because one moment you'll measure one current and the next minute you'll measure another current, and we can be talking about single-digit microamps, so 2 or 3 microamps, just because there's some contaminants on the board. And so what I do is I use a detergent, Electrolube SWAS detergent, in an ultrasonic cleaner for 10 minutes or so on about 40 centigrade. And then I do a couple of rinses of the boards in deionized water and dry them off. And a couple of ways you can dry them off. The quick and dirty way is to use your hot air iron, which for small boards is such as breakouts is a pretty convenient way of doing it. Or you may want to put them in an oven of some sort, just to let all the excess water, make it so it evaporates. So what are the drawbacks of that 2017 design that I mentioned earlier? Well, when I originally picked that microcontroller, data sheet, I did mention this at the time, the data sheet for the microcontroller had a sleep current of 60 nanoamps, but I measured about 500, and interestingly enough I just looked today and the data sheet has been updated, and they actually measure it now at 630 nanoamps. So I don't know if they saw my video and they thought that not much change. So I'm just raising this because, as in the previous video I did, as I say, I will mention this in the description and give you a link to that. It's one of the concerns is that the data sheet, take what's in the data sheet with a pinch of salt, measure everything yourself empirically. Also with that device, the low power oscillator is relatively power hungry. You might not think 170 nanoamps is much, but there are some other options available now. And the other thing is that I was running separate divider chains running off this 32 kilohertz low power oscillator. So I had a tuning fork crystal on the device, and not only was that running the RTCC through a divider, it was also running the LCD through a divider. So you've got some dynamic power consumption there. There you go, I've mentioned that. So that's just a quick overview of what the drawbacks were. And Let's now go on to the hardware that we're looking at here. So I've got two options here. You see there's a 4-digit version and a 6-digit version, and I'm using a PIC 16LF1907 or a PIC 16LF1947. The code for this, by the way, will fit. There's some other devices, I think 1904 and 1946, which are slightly cheaper and have less memory, and the code will easily fit in either of those. So if you have those instead, but they must be LF variants. I mentioned earlier on about the regulators, the PIC 16F. They will have internal regulators inside them, and so just be aware of that. And that we're talking orders of magnitude more current, so avoid and use the LF versions. And I've measured the sleep current on both of these devices at around 15 nanoamps, for pretty much the same for both of them, both at 1.8 volts and 3 volts. And another way of reducing power consumption might be to see if we can run it at 1.8 volts. This is something which I hadn't really considered before, but I just assumed that LCDs, they need certainly going back to many decades ago, I have this vague recollection that LCDs needed a fair bit of voltage to be able to run. But actually I did an experiment just to see if I can drop the voltage, and actually at 1.8 volts this particular LCD on here, which I'll note later on in the video, will run perfectly well at 1.8 volts. So that's a substantial reduction in your dynamic power consumption. And another thing is that, well, let's say we're running off of a 3 volt, as I said, these are running off of little button cells. They're put in heat shrink here, but these button cells are 3 volts typically, the lithium button cells, but if we delivered 3 volts to the PIC, which is perfectly valid, you can do that, you're going to hit additional current, because the dynamic power consumption is going to go up in proportion to the voltage applied. So although you could run the PIC directly at 3 volts, as we did before with the original 2017 version of this, the issue is that that's going to hit you in power consumption. But if you can run your LCDs at only 1.8 volts, then why not use that? And in addition, as I mentioned before, we now have voltage regulators around which we didn't back in 2017, which are in the tens of nanoamps. Now I should just mention, I've discovered recently that this microchip MCP1810T, which I've been using quite a bit in the last couple of years, because of its ultra low current consumption, is now end of life. So I do apologise for that, but Texas Instruments has got one called TPS7A02. They've got an 18 volt version of that. Both of these are available in SOC23. This one's available in SOC23 3-pin, which is what I'm using here, SOC23 5-pin as well as a DFN variant as well, which is I think it's got a feedback pin or whatever. It's got additional some additional functionality. There'll be a shutdown on the devices with extra pins. Similarly, the TPS7A02 in the SOC23 5 has got a shutdown, I believe, on it. For this demo here, I'm using the MCP1810T because I have plenty of them in stock. So next bit is although this device doesn't have a hardware I2C, but this device does, but I'm using the I2C in software because unfortunately the I2C on the hardware I2C on this device is also on segment pins, and we're running out of segment pins when we're particularly in static configurations like this, static LCD configurations. So there's a few other pins left over on this device, and which weren't segment or LCD pins, and I'm using those for a software I2C. And the buttons, which you may be able to see here, there's 3 buttons here, and there's also 3 buttons probably underneath the wires here. They're on pins with internal weak pull-ups, and 2 of them are on IOC pins, so that's interrupt on chain. So the idea is that the devices can come immediately out of sleep as soon as you hit one of the buttons. so you don't need any polling in order to be able to come out of sleep to do that. On these additional saving of segment pins, this is a bit of a cheat, but on the 4-digit version I've combined the hours, sorry, tens of hours, A, D and E segments. Now that is because, if you think about it, right here, so the only valid values for the tens of hours on a 24-hour clock, so you've got a 7-segment display. My pen's not working. 7-segment display. So the valid options are 0 on a 24-hour clock, 1 and 2. And this is A, B, C, D, E, F, G. And you'll notice that if you have A, D and E are all have exactly the same values for 0, 1 or 2. So that's so in this case A, D, E all on. In this case A, D, E all off, and in this case A, D, E all on. So we can tie in the tens of hours, A, D and E segments to a single segment output on the PIC. So we save ourselves a segment. So including the colon, which is in there as you'll see, we have 27 segment pins required. In the 6-digit version, I did separate out the tens of hours because it might be in future that you may want to use these, and there was enough segment pins left over. But I do combine the col 1 and col 2. So col, you see there's 2 column segments there which are going on and off. So it's 43 segment pins in total. So this is on a 40 pin dip, and this one's on a QFP, LQFP 64 pin. Why didn't I use a more modern PIC 16LF1917? Well, I did some initial checks on this, and there's a high sleep current over 100 nanoamps. It's also got a VBAT on it, and I'm pretty certain, this is why I mentioned earlier on, that the VBAT circuitry that's on the chip means that it's not the most efficient. So there you go. And this is probably possibly the biggest change and game changer to this, is the use of an external RTC. So we're talking about this MicroCrystal RV3028C7, and the features that it has on there, it's 45 nanoamps at 3 volts. In fact, that seems to be around about the same. I did test going down to a lower voltage on the chip, and it's not far off 45 nanoamps when you drop the voltage down. It will operate from 1.1 to 5.5 volts. It's 1 part per million at 25 centigrade. Actually, I'm not sure if it is temperature compensated. Sorry, I meant to check that. I'm not convinced that it is temperature compensated. But at room temperature, 1 ppm. I think it's about 3 ppm aging per year as well. Now, here's another. I'm going to underline the big issues here. In the specs, it's got a push-pull clock out. Now, the reason that's useful is that if you use an open drain output, then you'd need a pull-up. And when the open drain output went active, it would obviously be dragging current through that pull-up resistor. So as we're talking ultra-low current, we need to bear that into consideration. I did try little things like increasing the open drain resistor up to, say, 10 meg. So you end up in that situation that rather than having a nice clean square wave, like this, you end up instead having a square wave that's sort of more like this. And the problem is that in this case, because it's not a nice clean fast rise time, you'll end up with inputs on your PIC being in the linear region. and actually that increased current not just because it had the resistor on the pull-up, but also it had the it had the overhead of being the MOSFET inputs gates on the PIC being in a sort of non-saturated or completely unsaturated, switched off if you like, scenario. So that's why the push-pull is so important. I don't use the in-to-output at all on this design. Not only that, but the clock out has a programmable and compensated frequency. So what in the factory, when the way they get this 1 ppm is they measure the device and they put in some compensation into an EEPROM on the chip, and when this device comes up on pair on reset, it loads the compensation parameters into its RAM and uses those, so that basically it either adds or takes away additional ticks in the to make it so it's even though it's only about 3 or 4 ppm crystal inside the device itself. These are tiny, by the way, these devices, and so you know, so it's only 3 or 4 ppm on the crystal itself. By having this compensated frequency, you get down to up to 1 ppm. There's also an optional V backup on the chip, and that allows you to trickle charge a capacitor. So if you have a super cap on there, for example, or even just a ceramic, say 100 mic ceramic, then that means that you can take off the voltage whilst, for example, you're changing the main battery, or for other reason there's an intermittent drop in power, and by the time you put your battery back on, main battery back on, the time will have been maintained within this device. I mentioned the factory offset calibration, which is a compensated frequency, and I2C is the interface to it, and that has some negatives as well, which I'll mention in a moment. This device also has POR detection, so power on reset detection, included in it, so it knows if the voltage is either on the V backup or the main power itself, if you're dependent on that, has dropped below a certain value, it will flag that up, and when you boot or reset the microcontroller, it actually sniffs that out in the software and determines whether or not the time is actually valid. Some gotchas. I mentioned this I2C is expensive in power terms, which makes a difference as to how you design the software. So rather than going to the RTCC all the time, you actually maintain the time almost all the time on the PIC itself, because it's so expensive to go to I2C. I2C is a bus which has pull-ups on it, so I mentioned the pull-ups before. So oops, that's one, that's two. So you might have SCL, which is the clock, and SDA, for example, and this, because it's got these pull-ups on it, which might be, let's say, 10k, or maybe a little bit less, whatever. Because when you're typically these will just be high, both SDA and SCL. They'll be high. However, when in operation, of course, they'll be these will be going high and low, so you'll be dissipating power through these resistors. So rather than doing that, we could just maintain the time actually within the PIC itself, which is what I do. And one of the things that you need to do when your PIC boot or your microcontroller boots up is wait for the RTC to start up and refresh its RAM from EEPROM. So there's a sort of mirroring that goes on when the chip boots up, which not only takes this frequency offset calibration for the compensated frequency, but a number of other things as well. And that happens on power on reset, and it also happens every 24 hours. This is something that got me. I was debugging, happened to be working late at night, and suddenly I just noticed that the seconds were going up much faster than before. It took me ages to figure it out. And what happens at midnight, the microcontroller, sorry, the real-time clock, this MicroCrystal RV3028C7, it does another refresh of RAM from EEPROM, and that will change your whatever configuration you set up for things like the clock out is reset. So yes, you could override the EEPROM values as well if you wanted to. However, I've felt I'd prefer not to. There is a way to switch off this repetitive reset, by the way, which is in the code. It's commented in the code as such. You also need to realise that int and clock out are not mutually exclusive outputs. So if you configure the int, say, for something in particular, that might have an effect on clock out, but vice versa. So that's one of the reasons why I'm not using int, because I couldn't figure out how to use int and clock out at the same time without how I was using clock out. It was going to interfere with what int was doing. And also be careful to use low leakage caps on VBackup. If you use some caps, you'll lose potentially hundreds of nanoamps. So just be aware of that. I had a fair bit of luck using ceramics. I'd say 100 mic ceramic was reasonable. So your mileage may vary. And I've also noticed that vendors are not very good at being accurate with what you should to expect a leakage on caps, so probably do some empirical measurements would be wise. Also be aware that if you do want to use the automatic switching to the backup, it's going to use an additional 45 nanoamps is what I measured. So how did I do this? Well, I tied the RTC's clock out, configured for 2048 Hertz, to clock the microcontroller's LCD and also to the timer 1 via the T1 clucky pin on the microcontroller. Why did I choose 2048 Hertz, you ask? Well, the LCD controller on PICs in general, it has from whatever clock you're getting in the static. I'm just describing the static mode here. From whatever clock you're using, whether it's the secondary clock, say SOSC, or it might sometimes called T1 OSC, depending on the device, or for example your low frequency internal OSC, which is sometimes called LPRC. Anyway, whichever one of those, one of the first things it does is it goes through a divide by 4. This is in static configuration, and it then goes through a divide by 32, and so that means that on the output there it'll be whatever this is divided by 128. So what I had to do was to choose a frequency which was going to give us a fast enough LCD refresh that wasn't going to flicker as you have here. So I chose, but I also wanted to reduce the clock to the lowest possible on here to reduce the dynamic power consumption. So I went for 16 Hertz on here. So I think I've calculated this right. I'm going to probably have to get out the old calculator to make sure that I'm not telling you porkies here. So let's see, we've got 16 Hertz, 32 times, 4 times, there we go, 2048. Excellent. So we use 2048 Hertz in here. Good. So that explains the reason why. Oops. Why I chose 2.048 kilohertz. So the LCD runs at 16 Hertz. Now, when I first tried this, I could not believe the difference in power consumption I got off the LCD peripheral. It's significant. It's in the orders of hundreds of microamps compared to running it off 32 kilohertz. So it's a very significant difference. So that hopefully explains that. And then let's talk about the software. So we use the on-chip timer 1 that's on the microcontroller, clocked by external RTC to wake the MCU. So on the 4-digit version, I wake it up every minute. So this is this 4-digit version. It only wakes up once a minute. Now it still has a 2048 Hertz going into the timer 1. However, it doesn't wake up until it's done a minute's worth of ticking. So that's how that works. I think, from what I remember, that I had to use a prescaler of 1 to 2, and then that made it so essentially the prescaler would give it 1 kilohertz into it, and then I used 60,000 for the actual timing. So it has to go through 60,000 lots of 1 kilohertz before it wakes it up. A little bit different on here, because you'll notice that not only are we updating every second, we're also updating the colon every half second. So this wakes up every half second. So a little slightly different, although it still uses timer 1 as we did here. We have a different timing on there every time it wakes up. The time is maintained on the microcontroller because, spelling, sorry about that, I2C is expensive in power terms, as I mentioned earlier on. The exception is in the event of a microcontroller going to power on reset, or in fact any reset, the RTC is checked to see if the time is still valid. There's a flag called PORF which you can read out of the RTC, and it will tell you if the time is still valid, and if it is, it'll use the time out of the RTC chip. So that means that if you're using a V backup capacitor on the RTC, it will use the time that's set on the RTC. In the 4-digit version, oh yes, I mentioned this, we combine the AD and E segment for the tens of hours. And there's a 2 million to 1 duty cycle on this. So every 60 seconds it wakes up for 30 microseconds, which gives you an aggregate CPU usage of 250 picoamps. So that's tiny, that's insignificant in the big scheme of things. Now what I should mention is we're running at 16 megahertz. That was the most efficient, that's the clock frequency, so that's 4 MIPS in PIC 16 terms. So that's how quickly that runs. On the 6-digit version, as I mentioned before, we combine the 2 column segments, and we get a 16,000 to 1 duty cycle. Again, it's about 30 microseconds, but it's every half second, which gives us about 30 nanoamp aggregate CPU power. Which again, it's not insignificant, but it's tiny compared to all of the other stuff that's going on. So, as we will see. Also, it's not used generally, but there is I implemented in the software a low power delay. It's particularly for things when we're starting up and we're waiting for the RTC to go through its initialization and copy of EEPROM to RAM, and that can take potentially it's about a quarter or a third of a second. So I poll the RTC from the microcontroller. I think it's every 50 milliseconds, and I use a low power delay. So most of the time I'm running 16 megahertz, but I drop it down to using the low power internal oscillator during for those 50 milliseconds. Then turn on the 16 megahertz again, test again, drop down again as required. Now, of course, if the RTC was running and providing us with 2048 Hertz, that would be great, but on initialization the RTC generates 32 kilohertz on its if it's done a power on reset, the PORF bit is set, the frequency on the T1 clock input or the clock out on the RTC is 32 kilohertz. It's the raw oscillator frequency. Because I used a low power delay elsewhere particularly for the button pressing, I didn't want to have to deal with two possible options, so I went the cheap way and I just pole it using the LF Intos, on the basis that this is only going to be on power up when you put the battery in. I didn't think it was much of a big deal. Of course, it's something you could improve later if you wanted to. And of course the software I2C. This is some software which I pinched off of an earlier design which I'd done, so it literally was copy and pasted straight into here. I should add that the software is originally optimized for running at a 4 megahertz clock stroke 1 MIPS PIC 16. That was how it was originally optimized. I didn't do any changes to it, and it still works on here. So you may want to do, particularly on the timing side, you might feel it's not quite right. So this is what I mentioned on reset. The microcontroller polls the RTC on reset to wait for the refresh completion. So essentially for the RTC to initialize itself. And one thing that I store in when I build the source code is I put the compile time into the code, and if it determines that the RTC experience a power on reset, it uses that build time as the start time for when it initially switches on. So these are the two ways that it will use the compile time: if the RTC POR event happened, or the microcontroller's just been programmed, or indeed if it's a debug build. So if you're running in the debugger, you'll get that too. I should just mention that two of the segment pins that I use are shared with the debugging for the debugger. So just be aware of that, because you'll notice that a couple of the segments, if you're using the debugger or programmer with this device, will basically they show up as blank. So just be aware of that. I'm also using the M-Clear, the Master Clear button, as digital input, so that means that you have to disable the low voltage programming. So it's just something to be aware of. So what's the results? Well, I mentioned we use an LDO on here. Perhaps I should show you the diagram here. This is the LDO. So there's 3 volts in, 1.8 volts out. This is measured at the LDO's voltage input, 3 volts. 403 nanoamps average, with an average, the average is 19 segments on. I did a little spreadsheet to calculate that on a 4-digit display with a colon always on, and we got 1.2 microwatts, so a little bit over our 1 microwatt, and a 6-digit is 514 nanoamps with 29 segments on, or 1.5 microwatts. However, if you have 1.8 volts in existence, the 4-digit, so this is after the LDO, 385 nanoamps or 693 nanowatts, and for the 6-digit it's 498 nanoamps at 1.8 volts or 896 nanowatts. And you can add 45 nanoamps if you use the real-time clock voltage backup switching. So if you've got a capacitor on the V backup there. So I would say that's a success. If you wanted to be pedantic about it, you could say yes, if you supply this clock with 1.8 volts, both the 4 and the 6-digit will be under 1 microwatt. Why didn't I use a switching regulator? Easy. There are no switching regulators which operate at 20 nanoamps. As you can see, the difference between the 3 volts and 1.8 volts and the LDO's V in and V out, so the difference here between 403 and 485, 385, so it's 18 nanoamps was what the LDO was taking there. And similarly here we've got 514 at minus 498, so that's 16 nanoamps it was using in this case. So the 20 nanoamp suggestion is valid in my opinion. Some other improvements we might be able to do: sleep during low power delay, and use external 1 meg pull-ups instead of internal pull-ups. So this is really because when you press one of the buttons, the internal pull-ups are around about, they are at 1.8 volt VDD, they're about 50k. But on the other hand, if you think about it, how often do you press those buttons? It's very rare. The actual duty cycle when you actually use those buttons is next to nothing. So I would suggest not bother. Here's a little set of diagrams. So the top one is with the PIC 16LF1906, and the bottom one is with the PIC 16LF1947. And I will leave a link to where you can get these documents from. These are the buttons: microcontroller, real-time clock, LDO. This is the 7-segment display with the part number on it. Similarly, this is the one with the 6-digit version. So this is the 6 digits. This is 4 digits. And hopefully that explains it. If you need to know what the wiring is for the 7-segment display in the source code, which again I'll provide in the link, you'll be able to see that. So thanks very much for watching. And oh, I should just say, this here is the currently being drawn by the 4-digit display. So that's 380 nanoamps. And it depends on how many segments you've got on, as I mentioned before. So each segment takes about 10 nanoamps when it's on, ballpark. So that's reflected in here. So if you notice this going up and down a little bit, the reason is it's purely down to the number of segments that are on. So this has gone down a little bit now because we've got a 1 there, so it went from a 0 to a 1. So it's dropped down a few nanoamps. So thanks for watching, and hopefully you'll see that as a success. Cheers now.